Hello all, Dr. Caudell here. We're going to continue on in Chapter 6. So the next topic in Chapter 6 is calculating heat of reaction, now from bomb calorimetry data. So far in Chapter 6, we've done examples with a coffee cup calorimeter. So that's when we're told we're with a calorimeter or working with a calorimeter and we're at constant pressure. So now a constant volume calorimeter, we're going to come back and do examples with a bomb calorimetry style problem. So we've talked about bomb calorimetry, but now we're going to do a practice problem with bomb calorimetry. So with the calorimeter material itself can absorb some of the heat. If we're told the calorimeter material has a negligible heat capacity, then we don't have to worry about the calorimeter. But if we're not told that heat that the calorimeter itself can absorb is actually negligible, then we do need to take that into account in calculating the heat of the reaction, so usually what we're interested in. Heat, which is a form of energy, can neither be created nor destroyed. It can only be transferred between objects or from a reaction into an aqueous solution into the calorimeter material. So if the calorimeter itself is a necessary component to consider, then we're going to have the heat of the reaction, the heat of the water, and the heat of the calorimeter to consider. If we're working with materials or substances that have a specific heat capacity, so substances that have a value for their specific heat capacity, we know this is on a per 1 gram basis. So for heat of the water, we're going to have a specific heat capacity to work with. We recognize this is a specific heat capacity because the gram component is in this number. However, for a calorimeter, though, we have just heat capacities. It doesn't matter how much material is there for the calorimeter itself, we just have a heat capacity that we associate with calorimeters. So for some calorimeters, we just have a heat capacity, not a specific heat capacity. For a heat capacity, the units are just energy term over a temperature term. So with heat capacities, or capital C, we no longer have Q equals M cat. Instead, we don't need a mass term. So for heat capacities, the heat associated with something that has a heat capacity is just Q equals cat. So Q here is still going to be an energy term over a temperature term. That's that heat capacity, but not a specific heat capacity. So then to calculate heat for something that has an associated heat capacity, but not a specific heat capacity, then all we need is the heat capacity in energy per temperature multiplied by a change in temperature. Why does this work out? Well, heat is a form of energy that needs to just be in joules or kilojoules or some other unit of energy. Notice importantly, so an object with a heat capacity, we have no mass. So no mass is incorporated in this equation, just the heat capacity and the change in temperature will get us this value for the heat. Let's try this practice problem now. So we have a student who runs 2 experiments with a constant volume, which we know is a bomb calorimeter. This contains 1,400 grams of water. In the first experiment, a 6.000 gram tablet of benzoic acid is put into the bomb and burned completely with an excess of oxygen. Oxygen is one of our Brinkelhoffs, so it exists as a diatomic. Then benzoic acid is known to have a heat of combustion of 26.454 kilojoules per gram. So we need to pay attention to these units here. It's not per mole like we saw in the last part. So in part 3, this time it's in a per gram basis. We need to pay attention to these units. The temperature of the water is observed to rise from 11 degrees Celsius to 36.19 degrees Celsius over this period of time. So that's sort of the setup of the first experiment. Then in the second experiment, we have 5.520 grams of acetylene are put into this bomb and similarly are completely burned in an excess of oxygen. This time the temperature of the water rises from 11 degrees Celsius all the way up to 50.31 degrees Celsius. So these are the two experiments that the student does, then uses information and any other information we need to answer, is this exothermic, endothermic, or neither? Then calculate the amount of heat that was released or absorbed by the reaction in units of kilojoules. Then calculate the reaction enthalpy, so delta H of reaction, per mole of acetylene. So per mole of acetylene, it makes sense we want units of whatever energy term per mole. Now this looks like the balanced chemical reaction for acetylene and oxygen. So we notice diatomic oxygen here, acetylene. For a combustion reaction, which we just went over very briefly, it always produces CO2 and H2O, both as gases. Now this is balanced already. We can check, there's 4 carbons, there are 4 hydrogens, then 10 oxygen, 8 and 2. So this is balanced. If it were not, we would need to balance this first. So we were told the student did 2 separate experiments. So this was the first experiment in the setup of the problem. This first experiment helps calibrate the calorimeter. That is, a quantity of heat is produced that we can accurately calculate. Then by using this and the observed rise in temperature, we can then calculate the total heat capacity, or C-cal, of the calorimeter. What are going to be our units of heat capacity for the calorimeter? Is it joules per gram degrees C? No, right? For just heat capacity, we don't have a mass term. It's just some energy term over temperature. So heat capacity, just an energy term over a temperature term. Once we know C-cal, so the heat capacity of the calorimeter, we're not going to see a mass term in there, of course. We can then calculate the amount of heat released in the second reaction from the change in temperature, and that will allow us to answer the questions in the table. So we need to use this first reaction to first figure out what is the heat capacity of the calorimeter that we're using for both of these experiments. We know we put in exactly 6.000 grams of benzoic acid. We know benzoic acid has a heat of combustion of 26.454 kilojoules per gram. Well, we put in 6 grams, so we could calculate an accurate amount of kilojoules based on the true mass of benzoic acid that we put into this reaction vessel. So if we have the heat of combustion in kilojoules per gram, and we have 6.000 grams of benzoic acid, and this heat of combustion is specific to benzoic acid, we can set up the equation like this so that grams and grams cancel out. We want to know the accurate amount of kilojoules based on the true amount of grams we put into this vessel. This equals 158.724 just units of kilojoules at this point. So benzoic acid itself is responsible for releasing this amount of kilojoules. And we had 6.000 grams in the calorimeter, and we noticed that the water rose from 11 degrees Celsius up to 36.19 degrees Celsius. So really what we're setting up is the amount of heat lost by benzoic acid, or the amount of energy, then went into the calorimeter and the surrounding water, right? So we don't need Q equals MCAT for the benzoic acid because we actually already have units of kilojoules. We actually already know how much heat is released from the combustion of 6.000 grams of benzoic acid. So this is our Q value. This is going to equal whatever the calorimeter and the water are absorbing. Whatever heat is released from the benzoic acid is going to go into the calorimeter and the surrounding water. So this is going to equal the opposite sign of the benzoic acid. Now, typically, we've been saying that Q equals MC delta T. That is only when we're after a specific heat capacity, or when we're using a specific heat capacity to solve for heat. For us now, For a calorimeter, we no longer care about the mass, right? We just want the heat capacity itself. So we don't know the heat capacity of the calorimeter, but we do know how much heat it would be absorbing from the benzoic acid combusting, and we know the temperature change of the water. So we're going to use this information about the water and about the benzoic acid to find the heat capacity of the calorimeter. So as this combustion reaction took place, it heated up the surrounding area, including the bomb calorimeter material itself and the water around the bomb calorimeter material. So we're going to use information about the water and about the reaction happening within this vessel to get information about the calorimeter itself. So we're going to solve for heat capacity of the calorimeter. That's equal to then dividing the temperature onto the other side. So this is positive 158.724 kilojoules divided by the delta T. Temperature final of the water for the first experiment is 36.19 degrees C minus 11.00 degrees C. Now when we solve for this heat capacity of the calorimeter, it's going to be in kilojoules per degree C. This comes out to 6.30107 kilojoules per degree C. The reason we could use the first experiment to obtain this important piece of information that we need, so the heat capacity of the calorimeter, is because we knew exactly how much benzoic acid we put into this reaction vessel, and we know this given heat of combustion for benzoic acid in units of kilojoules per gram. That means that theoretically, when all 6.000 grams of benzoic acid are combusted, it's this many kilojoules per gram. And we could find the C-cal of the calorimeter because we know precisely this temperature change of the surrounding water. To bring us back to this setup now, so we do know exactly how much acetylene was put into the bomb calorimeter in the second experiment, but we don't know anything about the heat of combustion of acetylene. We could look up a theoretical value for enthalpies of acetylene, but we're going to calculate the experimental value of combusting acetylene in this specific calorimeter. This is pretty standard when using a calorimeter, so you want to use something initially where you know its exact heat of combustion to then sort of calibrate the calorimeter. What is the heat capacity of the calorimeter, so then we can use that information for our actual item of interest. Because say, for example, we synthesize a new material and we don't know anything about its enthalpy or heat of combustion, then if we calibrate this calorimeter, we can then use that information to find out information about a different, maybe unknown substance. Here we could look up information about acetylene, but we're going to figure it out. We're going to calculate it based on this experimental data. So we have the heat capacity of the calorimeter. Now we can use this piece of information to answer questions about acetylene now, rather than benzoic acid. So when we have just a heat capacity, not a specific heat capacity, we're going to just say C-cal times delta T. We don't need a mass term because the heat capacity of the calorimeter is just in units of kilojoules per degree C. No mass is involved here. So in the second reaction, we have information about acetylene. We also have information about the temperature change of the water. Based on this temperature change of the water and based on the heat capacity of the calorimeter material, we can figure out how much heat is being exchanged. So we don't know this amount, but we do know the heat capacity of the calorimeter. The amount of heat produced is going to depend on the heat capacity of the calorimeter and by how much the temperature increased. How much did it change? So how much heat for the calorimeter specifically is based on the heat capacity we found on the last slide, so in kilojoules per degree C, and based on the temperature change in that second reaction. Temperature change, or anything with a delta out front, final minus initial, so T final 50.31 degrees C, T initial 11.0 degrees C. This is for the experiment number 2. So then we'll get units that make sense. Degrees C and degrees C will cancel out. We do subtraction here, then multiply it by the heat capacity of the calorimeter to get a value obtained of about 247.695 without rounding in units of kilojoules. So based on the heat capacity of the calorimeter and by how much the temperature changed in the second reaction, we know that this amount of energy or this amount of heat was involved. So now we still have to say, is this reaction endothermic, exothermic? It has to be one of the other unless a reaction isn't taking place. So it has to either be exothermic or endothermic unless there just isn't a reaction happening. So we need the amount of heat that was released or absorbed by the reaction in the second experiment. Then we need the reaction enthalpy, so delta H of reaction, in a per mole basis. This 247.695 kilojoules, that is the amount of heat involved in the second reaction. So that's going to go here. Then we can calculate the reaction enthalpy, so delta H of reaction. Once we know the sign of this and make sure it makes sense, then we can say, is it endothermic or exothermic? Exothermic will have a negative delta H of reaction or enthalpy of reaction. Endothermic, a positive enthalpy of reaction. So if we have how much heat was involved in the second reaction, and we need this though on a per mole of acetylene basis, we had this many grams of acetylene. We can use this gram amount to go into a mole amount and then calculate the delta H of reaction. I want to point out this extra piece of information here that's thrown into the question. It doesn't matter that it took place over 8.2 minutes. Why might that not matter? Well, temperature is a state function. What does that mean? If temperature is a state function, all we care about is T final minus T initial. It doesn't matter how long it took to get there. It doesn't matter if it decreased, then increased again. So just T final minus T initial, because temperature is one of our state functions. So let's convert this gram amount into a mole amount. The molar mass of acetylene, so 2 carbons and 2 hydrogens, so 26.0378 grams per mole. I like to write it out like this so I can see my units cancel out. So 26.0378 grams per mole. Then grams and grams cancel out, leaving just moles of acetylene that were involved in this amount of heat in the second reaction. So this now 0.21199 moles of acetylene. We want an answer on a per mole basis, and again we figured out how much heat was released in that second reaction based on the heat capacity of the calorimeter and by how much the temperature of the water increased. Just from that information, this should tell us, is it endothermic or exothermic? So we should know that based on what I just said. Let's talk about this calculation, then we'll come back to all the final answers together. So this amount of heat in the second reaction, kilojoules, the units are important because as you've seen, this is usually either in kilojoules or joules. Then this many moles of acetylene. So on a kilojoule per mole basis, this comes out to 168.38 unrounded still kilojoules per mole. Now we know the sign of delta H should either be negative or positive. Right now, as calculated, it appears to be positive, but we haven't really thought through, should it be positive? Because technically Q cal was this much heat. So Q cal is a positive, just gonna round for now, kilojoules. We are figuring out the enthalpy of reaction not for the calorimeter, but for the acetylene. That means that if we had thought about this ahead of time, we should really be using a negative value for the kilojoules. Why? Well, whatever happens to the calorimeter, the opposite happens to the reaction. So really the reaction is acetylene combusting. We have information about the calorimeter. That means the opposite must have been happening in the reaction. The calorimeter itself is not going to produce this much heat on its own. It can absorb this much heat, so that positive sign there, but it had to come from somewhere. It came from acetylene combusting. If acetylene combusting is losing heat to the calorimeter, that means we'll have a negative sign for the reaction involving acetylene. So really, this should be a negative sign here, right? Because Q of the acetylene reaction is negative. Q of the calorimeter, though, was positive. This would make this an overall negative kilojoules per mole. If we didn't connect that, we can still think about it after the fact. So we're always in reference to the system or whatever is reacting. Our system is generally our reaction. We are finding delta H of the reaction, not of the calorimeter, not of the water that surrounds it. We want delta H of the reaction of acetylene combusting. If delta H of the reaction is positive, when the enthalpy of the products is greater than the enthalpy of the reactants. Delta H is positive when the reaction absorbs heat. For combustion reactions, those are giving off a lot of heat. So generally, if you see that something is combusting, you should think an exothermic reaction. What's the sign for delta H for an exothermic reaction? So it's a negative value for the heat of reaction or the enthalpy of reaction. When the reaction releases heat, the enthalpy of the products must be less than the enthalpy of the reactants. This was mentioned a few times so far in the chapter 6 recordings. So here delta H would be negative if the reaction releases heat, which generally speaking for a combustion reaction, we are definitely expecting some heat to be released. So in this case, the system is releasing heat. The reaction itself is releasing heat. We know that because it's a combustion reaction. We also know that because the temperature of the water increases. The temperature of this water increases, that had to come from the reaction itself. The reaction had to be releasing heat. Because where else would this temperature change come from, this temperature increase? It's not going to come magically from the material of the calorimeter. It's going to come from the reaction itself releasing heat. That's another way we can tell that that delta H of reaction should be negative for this combustion reaction of acetylene. So a few different ways to come to this conclusion where we know that delta H of the reaction of the combustion of acetylene is going to be a negative value. That also means it corroborates what we thought, where it's going to be an exothermic reaction because there's a combustion taking place, heat is being released, and we could see that from the temperature increase of the surrounding water. So that was a bomb calorimetry example. The important part we needed to do was remember that we're going to find a C-cal, so a heat capacity. So we'll be working with heat capacities, typically for bomb calorimetry style problems, where again, we don't have a mass that's included. If you were given a heat capacity of the calorimeter, you could basically start at this second experiment step. So if you knew the heat capacity of the calorimeter, you knew the change in temperature, that is the heat involved with the calorimeter. Then the heat involved of the reaction is the opposite sign from what you see from the heat of the calorimeter. Then with Q of the reaction, you can still equate that to mcat. So if needed to, you could also solve for the mass of a reaction. So there's a few different ways you could see these styles of bomb calorimetry problems. It's definitely exothermic. We found this heat amount and we found the enthalpy of reaction, so that negative value there, and with just 4 sig figs, all the correct units here, that is the answer to our problem. Just to reiterate again, if you have any questions about any of these problems, definitely let me know. So next we're going to go into this topic on using Hess's law to calculate net reaction enthalpy. Hess's law is sort of a puzzle-like problem, so I'll show you what we mean in a practice problem. Before going into that practice problem involving Hess's law, let's talk about the enthalpy of formation. So we know enthalpy, it's at a constant pressure. Enthalpy was talked a bit about in part 3. So enthalpy, a constant pressure, and the heat exchange. This idea of enthalpy of formation is what we're going to talk about here. So because there's no way to measure the absolute value of the enthalpy of a substance, do we have to measure the enthalpy change for every reaction of interest? Well, the answer turns out to be no, which you may have guessed how this was worded. So instead, we can establish an arbitrary scale with the standard enthalpy of formation. We denote the standard enthalpy of formation as delta H, so that's our enthalpy change, F down here as a subscript for delta H of formation, then this 0 here as a superscript, that usually just means a standard. So standard enthalpy of formation, you will see denoted like this. Let's define this importantly. The standard enthalpy of formation is the heat exchange, so we got that from enthalpy, that results when 1 mole of a compound is formed, so that formation, formed from its elements at a constant pressure. Here, a standard pressure of 1 atmosphere. The standard enthalpy of formation of any element in its most stable form is exactly 0. Oxygen gas, its most stable form is diatomic oxygen. The enthalpy of formation for diatomic oxygen is 0. Then the enthalpy of formation, though, for ozone, or O3, is a much larger value. Another example for carbon, the enthalpy of formation for carbon as far as a graphite material, so it makes up pencil lead, is 0. It's the most stable form. But carbon also makes up diamonds, but the enthalpy of formation for diamonds is a much larger value than it is for carbon in the form of graphite. So the standard enthalpy of formation of any element in its most stable form is 0. Sometimes we don't always know just by looking at something if it's in its most stable form. A good inkling is that anything that's a Brinkelhoff, its most stable form is a diatomic. So then its enthalpy of formation for these Brinkelhoffs that are in their Brinkelhoff form is 0. So we know carbon within graphite, oxygen gas, and liquid mercury, actually, that's the most stable form of mercury as a liquid. They all have standard enthalpies of formation of 0 kilojoules per mole. So pointing out the units here again, it's similar to what we saw for enthalpy of reaction. So the standard enthalpy of formation, this is also in units of some energy term than per mole. The standard enthalpy of formation of a non-standard element or a compound may be a positive or it can be a negative value as well. It depends on the stability of a certain compound or molecule in that standard state. Notice for water as a gas and a liquid, these are both non-zero standard enthalpies of formation. That's because water is made up of both H2 and O2, so really the form of H2O is not the most stable form of these individual elements. So the standard enthalpies of formation for water have a non-zero value. Then this negative sign for delta H of formation, that means that energy is released upon formation. So while the most stable form of hydrogen is definitely H2, and the most stable form of oxygen is definitely O2, when these two are close enough in proximity to bond and form water, that is a very stable form of both of these elements together. Individually though, H2 has a standard enthalpy of formation of 0, and O2 has a standard enthalpy of formation of 0. For a positive enthalpy of formation, this is when energy is needed or absorbed upon formation. So we can have enthalpies of formation for these individual atoms and elements. We can also have enthalpies of formation for things like water. So two different elements coming together. They can be negative and positive signs, so let's keep going. We set the stage for the standard enthalpies of formation. We also have standard enthalpies of a reaction. This is denoted as delta H naught, so delta H naught sub reaction. So not necessarily forming a substance, but looking at the standard enthalpy of the reaction now. Again, when you see these kinds of problems, we're more than likely assuming we're at constant pressure and we're at 1 atmosphere. Otherwise, we can't get a value for the standard enthalpy of reaction or standard enthalpy of formation. It has to be at 1 atmosphere. So we're going to practice calculating these standard enthalpies of reaction. And let's say we have importantly, again, a balanced chemical reaction. With a balanced chemical reaction as the molar coefficient A, then this is compound or molecule A or atom A, B, then B, C, C, and D, D. So these are our reactants, these are our products. To solve for the standard enthalpy of reaction, we can follow this formula. We're going to take the molar coefficient out front for that product, then multiplied by the standard enthalpy of formation for that product C. That's going to be added to this molar coefficient out front for our second product, then times the standard enthalpy of formation for that second product D. This is subtracting now the molar coefficient of this reactant times the standard enthalpy of formation for this reactant, but plus then, wow, that is a bad typo. I'm sorry about that. This is the standard enthalpy of formation of this reactant B, and then this molar coefficient B here for this reactant. So I apologize. I will definitely fix that. Generally, we have seen final minus initial. This is the same thing, right? We're taking products minus reactants. Another way you may see this represented, this is the same thing. We have delta H of the reaction, so standard enthalpy of the reaction is equal to the summation, so that's that symbol here. The summation of the molar coefficients of all of our products, the molar coefficient times the standard enthalpy of formation for each product, and we sum all of those, minus the summation again of the molar coefficient times the standard enthalpy of formation for each reactant. We might not have 2 each time, so this is a more general way to see this formula. We're going to practice using this formula too. Let's come back to Hess's law for a second. So Hess's law, when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So if we had the enthalpy associated with step 1, for example, and step 2, we could add these two together to then ultimately get the standard enthalpy of the reaction. So we take this information in step 1 plus this information in step 2. That's still going to give us our ultimate enthalpy or total enthalpy of the reaction that involves step 1 and step 2 added together. We'll see an example of this and we'll do a practice problem. If it doesn't matter exactly what happens in step 1 or step 2, just what we get to in the end, does this ring a bell? So enthalpy is another one of our state functions. It doesn't matter how we get there, only where we started and where we end up. So we'll do an example of Hess's law, and we'll come back and do an example using this formula too in the next part in chapter 6. So for example, if we wanted the standard enthalpy of reaction for this total reaction, we can piece together, this is what I was saying is kind of like a puzzle, we can piece together these three reactions. Do we need to reverse one of them? Do we need to multiply any of these molar coefficients by 2? Then we take the enthalpy for this step and the enthalpy for this step and this step. We may need to change the signs. We may need to multiply by 2. Then we end up adding all these together to get the total standard enthalpy of the reaction. I first went through what it looks like to change the sign for delta H and maybe multiply or change this molar coefficient in a previous part in chapter 6. That information should be in part 3 of chapter 6. For example, then, let's say these reactions were already set up fine. We didn't need to change the sign or multiply any of these values by 2 or 3 or 4 or divide by 2. Let's say they were all set up as they should be. That means we can find the standard enthalpy of the reaction by adding this delta H plus this delta H plus this delta H to get the standard enthalpy of the reaction for this overall reaction. Just as another review here, a negative delta H is going to be an exothermic process, right? Even for the standard enthalpy of the reaction, the signs still hold true. So negative sign here, an exothermic reaction overall. Let's practice now. So we have a lead acid storage battery. There are two reactions that take place during discharge of the lead acid storage battery. In one step, we have sulfuric acid. As a review, that's H2SO4, decomposes to form sulfur trioxide and water. Sulfur trioxide is a molecular compound, right? So we need to include that prefix there for 3, so tri. In another step, we have lead. This means lead metal, right? If it's not specified for anything, so just lead metal with that solid there. Another example of this, if we were told that copper reacts, that means Cu metal, so Cu solid. With lead oxide, lead 4 oxide, what does that Roman numeral mean again? That means lead is going to have a 4+ charge. Then oxide is 2-, right? So we're changing that ending to IDE. Doing the cross method here, this would be PbO4. These subscripts can be reduced though, right? So PbO2. PbO2 is lead 4 oxide. So just to review here a little bit back from chapter 2. Then we have sulfur trioxide again here, so it shows up here and here. This forms lead 2 sulfate. So lead 2 means it's going to have a 2+ charge from that Roman numeral that's indicated. We have to include those Roman numerals there because lead is a transition metal that can form more than one charge on its cation. It can be a +4 or a +2. Then sulfate, do you remember what that is? SO4 2-. Doing the cross method then, we would have Pb, then SO4, both with 2. That gets simplified though then, so just PbSO4. That is lead 2 sulfate. It's a reminder on how to read this chemical formula. We're going to calculate the net charge in enthalpy for the formation of 1 mole of lead 2 sulfate. So we want 1 mole of lead 2 sulfate. In this balanced chemical reaction, we should note that this molar coefficient right now is 2, but we'll deal with that as we're solving the problem. And also as a reminder from part 3, this delta H here for the reaction, this could be read as negative 775 kilojoules for every 2 moles of lead 2 sulfate, or then for every 1 mole of lead metal. Okay, so this delta H value refers to our balanced chemical reaction. So this holds true for every 2 moles of lead 2 sulfate, 2 moles of sulfur trioxide. So we need to be really careful here and be sure to take into account these molar coefficients in this balanced reaction. So Hess's law for our puzzle kind of problems, Hess's law states that the net charge and enthalpy of a sequence of chemical reactions is equal to the sum of the change in enthalpies during each step of the sequence. Something we could see is that if a particular step runs several times during the same sequence, its reaction enthalpy is added once for each time it runs. For instance, if this ran and then this ran, but then this ran again, we would still need to incorporate delta H here and the same delta H here. So for each reaction, we'll have an associated delta H. If that reaction happens twice, then we need to account for that by incorporating this delta H twice. Let's start solving our practice problem, and hopefully this will become more clear on how we apply Hess's law. So we want to know information about lead 2 sulfate, but we have these two reactions to think about, each with their own different delta H or enthalpy of reaction. Also to point out here, we're calculating the net change in enthalpy for the formation of 1 mole of lead 2 sulfate from lead and lead 4 oxide and sulfuric acid. So we want to know on a per 1 mole basis, but for this reactant and this reactant and this reactant is an entirely different reaction. So we need to find a way to combine these two reactions to then find information about this product. So as we're looking about how we can combine these two reactions, one thing we should note is that this sulfur trioxide shows up here and here. So first it's a product, then it's a reactant. This is what's known as an intermediate. It's not going to show up in our final reaction. At this point though, there are 2 moles of sulfur trioxide in this balance reaction and only 1 mole here in this balance reaction. Before combining these two delta H values, we need to account for that, because this value reflects 1 mole of sulfur trioxide that is produced, but this delta H reflects 2 moles of sulfur trioxide that are consumed. Whatever is produced in the first step has to get used up or consumed in the second step. In order to make that happen, we need to multiply this top reaction by a factor of 2. What is that going to look like then? We'll have 2H2SO4 in its liquid state goes to 2SO3 as a gas, plus then 2H2O liquid. Do you remember what we do with that delta H if originally it is 113 kilojoules? If we multiply this whole reaction by a factor of 2, that means we need to also multiply our delta H by a factor of 2. So that delta H then equates to 226 kilojoules because we multiplied all these molar coefficients by a factor of 2. Then in our second reaction here, Pb solid, so lead solid, PbO2, also a solid, plus 2SO3 gas goes to 2PbSO4 solid. The puzzle component of this is figuring out how we can take these two reactions and either multiply through by some factor, divide through by some factor. We may even need to reverse these reactions sometimes. Ultimately, we knew we wanted to get rid of the sulfur trioxide because we're asked about per 1 mole of this product, but from this reactant, and this reactant. Sulfur trioxide was nowhere to be seen in that question. So here's the product we're interested in from this reactant, and this reactant. We do not have sulfur trioxide as part of what goes into forming 1 mole of this product. So because of that, we knew we wanted to find a way to cancel out the sulfur trioxide. We need to find a way to cancel out the sulfur trioxide when we end up adding these reactions together. When we add these reactions together, we're going to put all of our reactants on one side. So all of our reactants, all of our products from both of these reactions. Then we see, can we cancel out anything that shows up on the same form on both sides of the equation? Well, here is 2 moles of SO3 gas, 2 moles over here. That means we can cancel out 2 moles of sulfur trioxide because that shows up on both sides of the reaction. If this were still just 1 mole of sulfur trioxide, then we wouldn't be able to cancel out sulfur trioxide in its entirety. We'd have 1 mole on the reactant side, but 2 moles on the product side. So that's why also we had to multiply this top reaction by 2. We need 2 moles of SO3 to cancel out with 2 moles of SO3. When we cross these out and rewrite it, we'll get this as our final reaction with no sulfur trioxide to be seen. Then again, we started at 113 kilojoules for the top reaction. We needed to multiply all of that by a factor of 2. So delta H of reaction 1, 226 kilojoules. We didn't reverse the reaction, we just multiplied everything by 2. If we were to reverse the reaction, we would need to change the sign here to be the opposite. If this was positive and we reverse this reaction in order to cancel out sulfur trioxide, we make this delta H now the negative version of that number. Then for reaction number 2, so delta H of reaction number 2, we didn't do anything to this one, right? So this one is just still a negative 775 kilojoules. Now, based on Hess's law, we can add these two together. We had to multiply this one by 2, then this one stays the same. That comes out to negative 549 kilojoules. Some Hess's law problems are a little bit more fun, right? We could reverse a reaction, we could multiply something by 2. Technically we multiplied this one by 2, but sometimes we do have to reverse a reaction to make certain products or reactants cancel out. So from Hess's law and from multiplying this one by 2, then adding this together to get the enthalpy of reaction for our overall reaction. Now we're not quite done with this one though, because this is the enthalpy of reaction for this final reaction. What do you notice about this molar coefficient for our product of interest? So this many kilojoules is associated now with 2 moles of lead 2 sulfate. We don't want to know this information for every 2 moles of lead 2 sulfate. We want to know the enthalpy for formation of 1 mole of lead 2 sulfate. So we can set this one up similar to what we did in part 3. This negative 549 kilojoules is for every 2 moles. But we want to know how many kilojoules for every 1 mole. We could also notice that we should just divide this value by 2, which is what we're going to end up doing. Technically, we would take negative 549 times 1 is equal to 2 times x. That means we need to divide this by 2 to again get this on a per 1 mole basis. So per 1 mole basis. So be really careful about these non-1 molar coefficients, especially when we're asked to solve for something on a per 1 mole basis. Whatever you end up finding out is for this form of the reaction. So if that is not a 1 out front, we need to account for that by, in our case, we took this number and divided by 2. So negative 549 divided by 2, then in the correct sig figs, that is negative 275 kilojoules. So rounding this number off into 3 sig figs, this is the end now of part 4 of chapter 6. Again, let me know if I can help with anything. Hope you're all doing well, and I will talk to you next time for more on chapter 6.